conductive oxide. So there's a special design, quite interesting. So I just show here. Okay. Still, they have SNO2, big particle, small particle TL2. So this is SNO2. And then this is TiO2. Okay? So TiO2 mixed SNO2. So if you look about the top side, you have SNO2. And you have TiO2. Okay, TiO2. But very special is there is a TiO2. TiO2, they deposit N2O3. Here is the TiO2. Deposit a thin layer of the N2O3. And then dye. Okay, and then dye. So this particle looks like it. Okay? Right? This particle looks like it. So based on the band structure, okay? Based on the band structure, you have this is FTO, conductive substrate, right? If we look about this band structure, here you have SNO2, okay? Right? So you have the SNO2. And then you have TiO2. But on the surface of the TiO2, you have Al2O3. Right? And then dye, the salt, dye. You have the dye. This is dye. Right? And then neutralize. This is the electrons. State. So you may curiously, because the Al2O3 is the insulator. Okay? So let's look at about this band structure. You can see that promote the electron to here. A, okay, first step to A. And then electron transfer to here, Tr2 conduction band. Through the Al2O3. Transfer. And Tr2 and SNO2 is like the brother ship, because similar band structure, blue phase. So the conduction band is similar. So therefore, it can transfer to SNO2. Okay? And then if you use Indian dot SNO2, that means you have ITO nanoparticle, right? Which has high conductivity. Do you understand? Which has high conductivity. But the problem is that you may ask me, Professor, Al2O3 is the insulator. How come electron can be transferred? Right? It will be blocked right here, right? But how come? That's a clue about the fabrication process. Okay. If the fabrication process can be achieved, okay, now the problem is how come Al2O3 can be penetrated? Why? We already talked about it in the chapter 3. In the classical and the quantum state, that's a difference. Electron transfer is a difference. For the classical, if I run and then to hit this wall, and then I will hit back, right? But if this wall is very thin, in the quantum state, this thinner wall can be penetrated, right? We call this is the tunneling effect, right? Tunneling effect, quantum tunneling, 量子穿隧, quantum tunneling effect. So Al2O3 should be thinner enough to make electron can transfer through this tunnel. And then you may ask me, of course, they will be recombined to this state as well. But the problem is that, here has a high conductivity, right? So electron prefer to transfer to here, not to here, right? Because they still have some impedance to transfer back, right? So if they can penetrate through the Tr2, and then because from here to here, the impedance is much lower than this purple color, right? So it will be transferred to this way, much faster, much straightforward, okay? Straightforward. So this is only the case, only the idea is something like that. But you may ask me, Professor, how to do the aluminum oxide coating, right? Aluminum oxide coating on the nanoparticle, you can do some of the stopper process, solution phase, okay, using the solder process through stirring, and then using some solution of aluminum solution, just like titanium dioxide, you can use the TTIP and then to precipitate the Tr2 on some of the high surface to volume ratio of the particle. So this is able to do. Okay, you can use some precursor of the aluminum oxide and using some stirring process, and inside you mix with the Tr2. So therefore, aluminum oxide could be formed very thinly on the surface of Tr2. It's possible. Okay, so this is able to achieve such phenomena. Okay, understand what I mean? So you have some state A from here to here. Okay, promote the electron, and B is the recombination. C is the charge transfer through the Tr2 conduction band. D transfer to the conduction band of SNO2. Okay, and then E is the recombination to electrolytes. F is also recombination to the oxidation state of the dye. Okay. So there's a B, C, D, E is right here. Okay, you can read by yourself. A is the excitation of the dye. B is the excitation dye decay to the ground state. C is the electron turnover. Okay, careful, turnover. Turnover in the Al2O3 layer to conduction band of the Al2P. Okay. D is the electron transferring to the conduction band of the DlSNO2. Okay. And then recombination with the electrolytes. E. Okay, this is the electrolyte. Recombination of the dye. Oh, this is F state. G is the regeneration. Okay, regeneration of the oxidized dye. This is provided by I minus reduction state of the iodine. Okay, is that okay? So this is the last slide. Just tell you about the silicon solar cell and disensitized. There's a very special, interesting feature is for the silicon solar cell, high thermal issue become drop because the thermal will making what in the silicon substrate thermal issue. We're making the dangling bond formation. Okay, dangling bond formation. So therefore, you can see right hand side. If the temperature increase, okay, actually the blue side, blue color is the silicon cell. STI is this is the institute in Australia. Okay, solar. There's an institute, solar research institute in Australia. They use in the titanium dioxide solar cell. That means the DSC for the red color. Okay, for red color. Okay, for red color. So red color you can see as the increase this is the temperature for red temperature to the 60 degree. As you can see for the DSC, you can see oh, the efficiency is high as it increase to 60 degree, right? But for the silicon solar cell, you can see temperature increase, the efficiency is drop. Okay, this is because of the as I mentioned, if the solar cell has been always has a high temperature, you know, at the summer actually, silicon solar cell surface can reach over there maybe 70 degree surface because it is quite hot. Okay, it is quite hot on the surface. So therefore, it is looks like an aging process, annealing. I would say an annealing aging process. So therefore, it will be for a long time. For a long time, if you find that after the solar cell being established, installed for a long time, actually the progressively power output will be dropped. Okay. But for the temperature, disensitized solar cell, the temperature increase, the efficiency is increased. This is as I mentioned previously, that because of the electrolytes, you know, because the electrolytes has a high viscosity. Right? So if we increase the temperature, viscosity will be reduced. Viscosity, you know? Right? 粘滞系数. Viscosity will be reduced. So viscosity reduced, that means electron transfer. Electron transfer, yeah. The carrier or the lithium, or sorry, not the ion or electron transfer in such electrolytes will be fast. At low viscosity. And this is also the output versus the angle. Okay? So for example, this is the solar light. I face the solar light, right? So I face the solar light, so therefore I get 100% output. But once the light, the solar tilt the angle, right? Based on the silicon solar cell, I have to apply the tracer. You know the tracer? Tracer, that means to follow the angle of the solar light, right? So always that the solar light can face radiate to the surface of the solar light. So you can get the more optimal output because the light is just radiating to shine into the surface. But if you don't have the tracer, for example, in the morning, the solar is right here, But at the afternoon, solar is another way, so you don't have the output, right? But after you apply the tracer apply is quite simple, but you need to apply cost, right? You have to apply cost. But as we mentioned in the previous slide, DSC, because we can do in both sides, right? Glass one side, another side is also glass. So they have the bifacial configuration. Bifacial, right? Bifacial. That means both sides has an efficiency, has an advantage to have some radiation. So that's great. That's why I would say this is the angle incidence. I would say this is something like the angle sensitivity, solar light angle sensitivity. If the angle is too sensitivity, that means once you face to another angle, and then there's no efficiency output. So I would say the lower sensitivity of the light would be better. Okay. So DSC has such advantage. Okay. So that's everything of this chapter. So I would say because now it is although DSC right now maybe you can't see any commercial product compared to the silicon. But this is a very interesting and also theoretically interface issue. It is quite important, especially for some, because we are studying this is something like a book, a text. Okay, it's a prose. So I wanted to deliver the more fundamentally the chemical or physics issues. So that's why I select DSC. Okay. So of course, still you may discover a lot of the different solar voltaic, okay, photovoltaic, maybe organic, okay, and also perovskite, okay, as well. But they are doing the same concept, just modify the structure. So if you know about the mechanism of the DSC, if you read the perovskite solar cell, that will be more easy to understand. Okay. So because of time limitation, we don't have the time to show another something like the organic solar cell. So let's stop here regarding the organic solar cell. I will stop here. So let's continue to the chapter 7. So chapter 7, I will talk about regarding this very important research for the piezoelectric materials as a generator. Okay, as a generator. Just like yesterday, okay, this week, right? This weekend we have a conference. Okay, we have a conference, and I invite Professor Zhou Wang. Okay, Professor Zhou Wang. He is pioneer to develop the first nano generator using piezoelectric materials, such as very simple material, zinc oxide. So he discovered zinc oxide nano-wire, single nano-wire, and then using the AFM tip, okay, conductive AFM tip to apply the nano-wire of the zinc oxide, because the zinc oxide is a piezoelectric material. So he applied, the scientists applied the nanowire and then generate electricity. Okay, generate electricity. So this is been published in 2006. Okay, in Science. So at that moment, create a huge, interesting research regarding, maybe if that is possible to apply force on piezoelectric materials. And then it is a lot of the imaginary image to think about, there is electricity can be produced in everywhere. Do you know why? As long as I produce a nanowire, because he applied using the AFM tip to contact, and then just bend it. Just bend it. and it generates electricity. Generate electricity. So therefore, if you look about, oh, if there is a sun, you know sun, just I'm talking to you, I send the some frequency, sonication frequency. Just my sound, my voice is very low frequency. But if you think about if there's a high frequency, okay, any high frequency or any all frequency, there's a very noisy, right? So you can have it, this nanowire, right? And you just have it making a device, right? And then contact each other. This is a device, okay? So that is possible to generate electricity. So you just put a device somewhere, right? And then you connect to the battery. So therefore you can charge this capacitor, right? You can charge this capacitor. So this capacitor can be charged and charged and charged and charged, right? So because you know the mechanical power, mechanical energy is every time, it's everywhere, right? So you don't have any limitation of the solar radiation just only 8 hours, 6 hours, 4 hours, right? So you have a lot of the image, right? You have a lot of image. So at that time, it discovered this and then increased a lot of the research. So some of the materials, not only the oxide, but also some of all the piezoelectric materials. Like indium nitride, like gallium nitride, like some of the ferroelectric material. Okay. All of them, as long as it has a piezoelectricity, it's possible to produce electricity. Okay, so Professor Zhongling this Sunday, okay, just yet Sunday has given a very significant talk regarding all the history of the nano generator. So in the very beginning, he using the dioxide nanowire to do the piezoelectric nano generator. So I have a chance also to visit his lab in 2011. Okay, we're using the VNSL3. So this chapter I also will discuss about this. This is the ferroelectric material, okay, which can also generate electricity. Okay, generate electricity. And then also 2012, okay, 2012. In also my visiting period, there's some research also doing the which tribal electrical nano generator. So tribal electrical nano generator is a difference to the piezoelectrical nano generator. Piezoelectrical nano generator, you need the materials as piezoelectricity. Okay. Later on, I will show you what the materials has a piezoelectricity. Okay. Some later slide I will show you. But for the tribal electrical nano generator, you don't need any piezoelectric materials. You just need to bring different charge surface, so-called positive charge surface and negative charge surface. They brought together and can produce electricity. So as you can see, you know, your hand is a positive charge. Your hair is positive charge. But in general, plastic, you know the plastic. Plastic is a negative charge. So you may be curious, what is positive, what is negative? That's very simple. Negative charge, that means this material is easy to get the electron. So therefore carry negative charge. Do you understand? And your hand is easy to donate the electron, so carry a positive charge. Do you understand? Okay, so that's in all the Earth, all the substance, you have many kind of the materials. So that's why if you are, when I was a kid, okay, I used plastic to rubber, okay, the tactile, right, and then making the plastic become very strongly negative charge. So therefore, if you have the some of the hair, okay, so the hair can stuck in on the plastic. So that's electricity. Just we call this electricity is the static electricity, 静电, okay? So static electricity also one of the electricity, right? Just at the, because this is the fresh tribal already been discovered 100 years, but there's nobody, no scientist can be functionality to become making the device can be useful, okay? So this scientist, Professor Wang, used these materials, tribal electrical nanogenerator. I will show you about, there's a tables, okay, can do that. Okay, you can do just in your home, in your lab, as long as you use the lab, plastic and glass, okay, you cut in together, you can have electricity. So very easy, simple to find. And these materials, okay, this generator can be cell power, can use the cell power, we call so-called the active sensor, okay, active sensor, and then even can be used as a contact electrification, okay, FET device. Okay, we also have one paper to publish in nano energy, which is the FET device, okay, using a tribal electrical effect. Okay, so this chapter will be more, but I would say practical application. Of course, I will also explain, okay, introduce about some science, some fundamental of the piezoelectrical materials, especially. So the background is, you know, recently, I would say for the all time, the materials research, we always talk about the processing, what process you do, right? What microstructure you have, right? Process, microstructure depends on the process, right? You are using a chemical process or physical process, CVD, or some of the something else. There's a lot of processes which can justify about the microstructure. Right? The microstructure can be particle size, grain boundary, and also phase, right? Phase. So all the microstructure determine what process you do, right? And still, this microstructure will determine about the property, right? About the property, because the different microstructure have different property, right? So you have a lot of the property, maybe in the materials. You have the optical property, you have the magnetic property, right? You have the thermal property, right? And what else? What else? Mechanical, magnetic, right? And yeah, mechanical property. Mechanical, that's about the strength, right? The strength. Mechanical property, optical property, magnetic property, and thermal property. That's it, right? So we want to understand about what property we have, right? Based on your synthesis. And then still we have to know, understand the performance. We want to determine the best performance, right? We want to determine the best performance. So the best performance, all of them, process, microstructure, and property, we have the performance. But even now, you have the higher performance. Still, you have to consider about the cost, right? The cost issue. So whatever you design, energy materials, biomaterials, and architectural complex materials, all of them you have proceeding with the same procedure. Okay, looks like that. Okay, so, but now we are facing an issue, right? I think at the first chapter I will have already shown you about the electronics waste, right? Now the electronics waste is a huge category, right? You have huge different size of the battery, right? So this battery, sometimes this battery, I would say, can recycle. You can recycle the battery, but you have to consider how much it will cost to do such recycle. Right? If the cost of recycle is much higher, and nobody want to do it because you have no money to get, right? So recycle becomes an issue. And there's a non-recycle. So how to do? You just throw away, right? If you throw away, and you will pollute the soil, you pollute the water, right? So drinking water is also very important, right? So, but anyway, the electronics is very convenient. You have the cell phone, you can do a lot. You can control the TV, control the air conditioning, control everything, right? It's very convenient for us. But soon after this, usually the cell phone, maybe 2 years, maybe 3 years, maybe 4 years, will be remodeled again. So you will buy a new one, right? You buy a new one. So what about the old one, right? Old one give you a mother, your mother don't want to eat. You want a new one. Everybody wants a new one, right? But therefore, there's a lot of the electronics waste in general, right? So to do such recycle is very difficult, right? You know, right now, in the previous 20 years ago, right, when I was young, I am just my age is similar to you guys, 28. We just talk about the TSMC is doing 100 nanometer. I would say the technology is 100 nanometer. That means the channel length. Okay, but now 20 years is 1 nanometer, 2 nanometer channel length. So such very short, very tiny device, it's very hard to do the recycle, right? There's no way to do the recycle because it's just very tiny. You can fabricate 1,000 million in a single chip. You can fabricate 1,000 million of the MOSFET. So to do such a recycle, there's no way, right? So how to do? It's become a serious issue, right? A serious issue. So such a serious issue, you still have a lot of the considerations, pollution of Earth, our Earth, right? Our Earth. So that's the problem we have to think about. Whether it's possible that some of the low power consumption device might be one day you can use the mechanical strength and then to lighting the LED, right? Or one day, if some of the low power consumption, because we have a lot of low power consumption devices. For example, your iWatch, right? iWatch, sometimes if the functionality is not too many, more simple, just take some exercises to make us, to show you how long you have the exercise, right? Show the mileage to you. That's maybe you just need to low power consumption. You don't need to do that. So if that kind of the low power consumption device, we can use some nano generator, which is if you walking, jogging, and then that can cell power together, cell power, which means to charge. And charge no need to the battery. You just need to provide a capacitor. You know, the device inside has a lot of the capacitor, right? A lot of capacitor. So the capacitor is good enough to provide electricity. So if there's no battery, that means after this device or this portable device, 2 years, after 2 years, you don't need to consider about the battery. right? So you have the very major part of the battery. You can reduce the loading of the recycle, or you have to throw away. Do you understand? And also, one of the possibility, if you let the inside of your portable device no battery, that means that you can save the space, right? You can save the space, which means that you have even more portable, right? Portable. The device can be smaller, okay? So this is a very one of the advantages. This is my work, 2012, okay? I used the single nanowire, and then just embedded on the plastic substrate. Okay, this is PS substrate, and then bending, generate electricity. This electricity can up to 0.1 voltage to 0.5 voltage. Okay, so this voltage, maybe you told me, Professor, this is so small, how to lighting the portable device. You have to look at about some of the sensor, biosensor. Okay, there's a lot of biosensor need to implant to the body to test. So this body biosensor no need high power. Okay, but still need to battery. So if we can do such device, okay, can save power. That means that we don't need a battery, right? So the device can make it more smaller. So it's easy to inject to your vessel, 血管, okay, to your vessel, right? Provide electricity, okay. So this is the biosensor. So at that time, okay, I visited 1 year. At the beginning, at the first year, okay, first month, do you know? I just show you my experience to you, okay? I doing the experiment, okay? I doing the experiment. I grow the nanowire on the substrate. This is a ZN-SN03. And then I want to demonstrate about how this single nanowire can be used as a nano generator. So I use like a paper, okay? Use a paper, and I use the paper very. This paper just looks like I'll show you, okay? It is very simple. You can do is this paper become very thinner needle, okay? Like this thinner needle, okay? And then under the microscope, okay, place this under optical microscope. And then under the microscope, I operate to touch this nanowire and then pick up. And because this is the paper, right? There's an electrical charge, right? Once the electrical charge pick up, and this nanowire is able to be break, and huge amount of the nanowire can be absorbed, can be electrical attached on this paper needle. And then I place, for example, this is plastic, and I place on the plastic substrate, because this is a plastic, it is the negative charge, right? So the metal oxide is a positive charge. So therefore, this metal oxide of the DNSNO3 will be spread on this surface. Okay? So therefore, under the microscope, I can observe this is a PS substrate, plastic substrate. And once under microscope, I press on it. So I will see a lot of nanowire. Looks like that. Okay? Looks like that. And I will choose one nanowire which is more parallel to this direction, to the x direction. Okay, to the x direction. Looks like, for example, I chose this nanowire. Looks like that. Okay? And then next is that I wanted to apply the contact electrode. So the contact electrode is that you have to use the silver paste, silver glue. You know the silver glue? Silver glue. So it's just like, you know, silver glue? This is the solution. Okay? So you can pick up a drop silver glue. Okay? Silver glue. And then under the microscope, transfer silver glue to drop to the substrate here. Okay? So this silver glue will be diffused progressively because it is a solution. Okay? And then it's a high viscosity. So it will diffuse progressively to touch this nanowire. Okay? And then you make a success to one point of the electrode. And then another is this point. Okay? This point. This point is quite important. If you drop too big, it will fully cover. Do you understand? So you have to be very careful to use this silver glue to drop to here. And then this silver glue will diffuse to here. Once the silver glue diffuse to here, and then you make success. Both sides has a conductive electrode in success. Next, make a wire bonding. Okay. So you can see here. Here is a conductive wire, right? Here is another conductive wire, right? Right? And then, right now here, you have DNSNO3. Do you understand? DNSNO3. Okay? So why I wanted to choose? Why I wanted to choose this nanowire should be in parallel? Because I wanted to do in the bending. I wanted to do in the bending. Once I bend, right, and then the growth of the nanowire, this direction, for example, this direction is a 001 direction, right? Because there is a preferred orientation, growth, right? So therefore you have the preferred orientation. Once I bend it, which means this O1 have tensile strength, right? This O1 they have tensile strength. So because of this nanowire, you have to understand the polarization axis. Okay, later on I will show you. The polarization is very important because the polarization determines about the electricity, what electricity will be generated. Okay, what electricity will be generated. So therefore, I do it in the first months. I do this generator to fabricate this generator, and I told my experience to you. I takes about over than 3 days. Okay, over than three days to fabricate only 20 devices. 20 devices. Finish. And I'm very happy. Finish 20 devices. Takes 3 days. Okay? You have to understand. 3 days, 1 day is not 8 hours. 1 day for me is 12 hours. When I am a visiting star. Okay? Maybe you guys, 1 day is 8 hours. No, 1 day is over than 12 hours. I work from the 7 to the from the day in the morning 7 to the evening 7. I still have no idea that to go home. So I work for a long time. Okay, 3 days. And then at that time, because I had to, once you finish it, you have to protect. I use the PDMS to protect. PDMS. PDMS is one of the polymers that can fix the nanowire, just like a package. Okay, just like a package. So it can fully, when you bend it, the nanowire will be not damaged. So it is a soft. PDMS is a soft. And then PS is right here. Okay. So PDMS, once you drop, because it's a solution, so you have to bring this device to the oven, anneal, right? And then solidification. Okay. So I asked one guy, he told me, so because I have no idea how, because this is my first time, I have no idea about the annealing temperature in order to solidify the PDMS. So I asked my colleague at that time. So he told me 100 degrees is no problem. Okay. So in order to make sure that it becomes safety, okay, more safety, because I take 3 days. So I use the 50. Okay, I use 50 in the oven. Okay. So I'm very careful to bring the 20 device into the oven. And then after 10 minutes, I come back to see, wow, the PDMS is not curing, but the PS is deformed because the temperature too high. Because at the level, I think that PS should be suffered at least 80 degrees. But we buy the PS substrate. The temperature is very low. So I wanted to cry. I take 3 days, right? I take 3 days, so it is a very difficult, hard time for me. So everything becomes 0, right? Everything becomes 0. So at that time, there's another postdoc told me, Professor Wu, because I'm already a professor in Fengcheng University, so he told me, Professor Wu, in here, we are doing a big job. We are wanting to publish other stable paper. So this is very general. My first time to doing such device, I take 100 device, and then I doing the same issue, right? So at that moment, I understand as a scientist, once you're doing the research, you have to suffer such struggle. Very important, because you have to do a lot of struggling when you're doing the experiment is a fail. If you're doing the experiment is success, right away, this is not experiment. You are doing the duplication, right? Just like your school, in the high school, in the juniors high school, you have to do some physical and chemistry experiment, right? You have a lot of, you just follow the procedure, right? You follow the procedure, so you always success, right? But you are doing the research. So doing the research is not one time, one shot success. Impossible. So the more important is that you have to struggle and suffer such, discouraging. Many times if you can suffer such discouraging, one day you could get the Nobel Prize, right? Okay. Okay, time's up. Okay. All right, so let's see you next week, okay?